afternoon. Now we will have the NPTEL Week 12 questions related to various aspects of powder metallurgy. And first, we'll try to solve certain MCQ based questions, and then we'll move to the numerical part. First question says that select the process suitable for making a powder metallurgy component of a high density with nano sized grain. So that means we are here concerned with the formation of a nano sized grains, and we need to know which technique will be more suitable. Is it just hot pressing where we are pressing the mold at a very high temperature to avoid the porosity and achieve higher density? Is it liquid phase sintering where we have a liquid as a second phase that results in the formation of liquid bridges between the grains, or a spark plasma sintering or powder forging? So the answer is spark plasma sintering, because this is a technique where we can achieve high at a very small duration, in a very small duration of time we can achieve a plasma condition, and that plasma will help in generating electric fields. And there will be two heatings, someone is plasma heating and Joule heating, and that will result in the sintering process, and we will be able to have a nano sized grains because the grain growth in such processes is restricted. Okay, so that means if we are restricting the grain growth, we are able to produce the formation of nano sized grains. Okay. So next question says that select the processes that employ a compacted pellet or a sintered perform during sintering. So you need to know which of these will use a compacted pellet during sintering. So normally we have a spark plasma sintering, hot pressing and powder forging and conventional sintering. It is actually only in the powder forging or a conventional sintering where the pellet is being formed prior to the sintering process. While in spark plasma or hot pressing we do not require such compacted pellets, but in powder forging and conventional sintering we'll always require a pellet or a mold to be formed, a compact to be formed prior to sintering process. So option C and option D are the correct options. Now, the next question says that during the sintering process, as the temperature increases, so we have a sintering process where we have increasing the temperature, the yield strength increases. But as you increase the temperature, there is a realignment and recrystallization of your grains, and that will affect your mechanical properties, which are yield strength, ductility, your the response to deformation, your plastic deformation. So it says that the yield strength increases, but as you increase the temperature, the yield strength does not increase. The yield strength actually decreases, because you know that yield strength is a property of your grain size, and it is proportional to your say for example grain size. Say for example, if you have a very small grain size, then you will have a very high yield strength, because you will have large amount of dislocations present that will be hindered, and there will be hindered diffusion of the dislocations, and that will result in your higher yield strength. However, if you have a high temperature and the size of the grains started to increase and started to coarsen, then the yield strength will decrease. The yield strength will not increase, but the yield strength will decrease. This is the right option. The next option was that diffusion decreases. This is wrong, because you know that as you increase the temperature, the rate diffusion rates also increase. So diffusion is directly proportional to your temperature. So with increase in your temperature, the diffusion rates increase. So it is they do not decrease. Okay. So this is wrong. And then we have another question that says that the rate of strain hardening decreases. So this is the right option, because the rate of strain hardening definitely decreases, because you will not be able to have a strain hardened material as the yield strength decreases. So as the temperature decreases, yield strength will decrease, the rate of strain hardening will also decrease. Okay, then we have another question that says consider the following statements regarding spark plasma sintering. So we have to say what are the characteristics of spark plasma sintering and which of the statements is correct. Is that there occurs vaporization, there is a faster diffusion. This is definitely correct because spark plasma sintering is a technique where we can achieve large amounts of like we can achieve the sintering temperature in a very smaller or shorter duration because we have a plasma and Joule's heating both acting together for the sintering process. So faster diffusion will occur and heat is highly localized, both joules and pulse mechanism occurs. This is also correct. And then based on the analysis we can say that the vaporization also occurs, the heating is localized because the only those materials are localized where the electric field interacts with the molecules or the gaps, air gaps, and in those air gaps there is a localized sparkling and that will result in localized heating. So heat is very localized because we do not operate here on the basis of your conventional sintering process where for example you have a material that is being heated, the heat will be transferred first to the container and then to your material and then it will be heated according to your sintering temperature. But in spark plasma what happens actually, the heat that you are giving or the plasma or the electric field that you are imparting on the material that allows the selective heating of these components or localized heating rather than heating of the container and then heating of the components. So it results in a faster heating and there is a faster diffusion in these cases. Next question says that consider the following statements. The densification is similar to plastic deformation at all pressures. Dislocation control processes has a dominant role to play in densification. Extensive plastic deformations of the particles can disrupt the surface films. Large shear strain disrupts surface films. So you have to say that which of the following is correct. So all the first two conditions are right because obviously if you have the plastic deformations, if you it says that the densification is similar to plastic deformation because if you increase the temperature after a point there is no further densification. So when you are trying to increase the pressure, the densification level saturates and they achieve the maximum at a certain point. So the densification is always similar to plastic deformation because you will know there is a similar stress strain curve for your plastic deformation also, that is there after a point it yields. There is no significant change in your plastic deformation with change in your strain or with change of your pressure. So the plastic deformation and the densification operate in a similar way with change in the pressure. Then there is another that says dislocation controlled processes has a dominant role to play in densification, right? This is true because if you have a dislocation controlled processes, then they will influence your movement of your dislocation. They will influence your grain growth. It will influence your particle sizes, and therefore it will help in your densification. So first and second option are the correct options. Then we have another question that says select the nature of the force applied during a conventional hot pressing process. Is it uniaxial, biaxial, triaxial, and isostatic? This is we know that it is a uniaxial process when you are having a hot processing process. You have a compact and you are trying to compress it uniaxially in one direction under a heated condition because it is hot pressing. So it was a uniaxial force that is being applied on your mold. Now, next question says that consider the following statements regarding hot pressing. The process is rapid, this is right, and then we have excellent control over heating rates. Dyes can be made using silicon carbide. Contamination from dye is not a serious concern. So this is statements that is the process is right, excellent control over heating rate and contamination from dye is not a serious concern. These are the process statements that are correct regarding the hot processing process. And then we have the correct sequence of events that happen in a spark plasma sintering is Joule's heating, plasma, plastic. Why is it that it first heats using Joule's melting and then through plasma heating and then there occurs a plastic deformation? or first by plasma, then by joules and plastic deformation, or first by, obviously this is not right because the plastic flow cannot occur first. There has to be a certain heating during the sintering process that will result in the heating of the material, and then there will be plastic deformation or plastic flow. And the last says that there is a particle rearrangement, plastic flow, and plasma. This is also wrong. So, in the, out of the first two, there is always a plasma heating that happens first, and then the Joule heating and plastic flow. While Joule heating does not occur first, because then there will be similar to your conventional heating, right? If your Joule heating occurs, then it is similar to your conventional heating. Okay, so if the plasma heating occurs, and then Joule heating occurs. So in the next process, the neck formation takes place in which stage of the SPS process? You know, in your conventional processes, we had different stages. We had initial stage, particle rearrangement stage, then we had a neck formation stage, then we had intermediate stage. So here you have to say in which of these stage is the neck formed? Is it during the particle rearrangement, Joules heating, plasma heating, or plastic deformation? It is actually only during the plastic deformation. That is where the process is very fast, because during the plasma. So we now have a numerical question, that is some very easy numerical question that says that the aluminum powder having an apparent density. So what do you mean by apparent density? It is a density that is of a loosely compact, that is before you have gone for sintering. So if you have a loose compact or a loose powder, then you have a density of the loose powder as 810 kg per meter cube. Okay, so this is your density for a loose powder, and it is compacted in a cylindrical die at 600 MPa. The density of the as pressed aluminum compact. So after you have pressed it, and now you have a green compact. So you have a green density, and that is equal to 1750 5. This is obviously higher than what it was for the loose compact, because now you have you have compacted it, and then you will have a higher density. If the height of the as pressed compact is 12 mm, that means when you have pressed it, the compact, that is, for example, this is your compact, and you have pressed it, and by pressing, then you have obtained a certain density of the material, and then the as pressed height is 12 mm. But you have to find what is the fill height. Fill height means what was the density when it was, sorry, what was the height of the bed before it was subjected to compaction. That is, when it was in this loose powder form, what was the height of the powder, or the fill height. That fill height is always represented for the apparent density, where the powder is loosely present in a compact. So you have to find a fill height. So this will be something H. Obviously H will be greater than the 12 value, because we are having a fill height before you are densified the material. So this will have a higher height as compared to this 12. So how will we find this? Simply we know that density is equal to mass per unit volume, considering, because we have same mass for the both cases, we will say that m1 will be equal to m2, that is whatever the mass is there before you have compacted the material, and after compacted the material the mass will remain the same. So we will say that density d rho 1 v1 is equal to rho 2 v2. So this is your formula that can help you to determine your height. So because it is a cylindrical compact, so you know we can change the volume to pi r square h. So we can write density 1, volume will be pi r square h is equal to the density 2, then volume 2 will be pi r square h 2. But because we are having the same cylindrical compact, the radius of the two compacts will be same, only the height will change, and because of the change in the height you will have a difference in your volume. So taking forward this, then we know what is density 1, we know what is density 2, because this pi r square are constant for both systems, we can cancel them out. So we know what is all of the parameters, we can find the value of h1. So your H1, that is height of your compact, will be equal to your density of the compact, that is green compact, green density, that is 1755 divided by your the density of apparent density, which is a loose compact, and multiplied by the height of your uh, asterisk compact, so that will be 12, and then therefore we will have a total height as 26 so this is your height of your fill capacity, your fill height, or the height of your when you are finding the parent densities. This is your answer. Okay. uh, Now, just similar question was also asked. These are some gate questions, and this question was asked where we have a metal powder and the apparent density is given, and it was compacted in a cylindrical die to a green density of 5.5 gram centimeter cube. If the green sample was 12 mm, then the fill height of the powder would have been. So now we have the same question, same approach. Now we have to again find the density of the before apparent density when the fill height of the powder. So we know that density rho 1 by V1, rho 1 into V1 is equal to rho 2 V2, because we are considering the mass of the powder to be same. The density 1 is given, so we can first write that rho 1 H1, because pi r square will cancel again, so this will be rho 2 H2. Okay, and then we can find the H1 as this will be 2.5 centimeter divided by the no 5.5 centimeter. Okay, so this will be equal to, this will be 5.5 divided by 2.5, and you know the height of the compact, that will be equal to 12. So the fill height will be 26.4 mm. Okay, this is your fill height for the sticks. The process was same, the approach was same. Now the height of this fill height is 26.4 mm. Then we have another question that says that the driving force for centering a compact consists of spherical particles of radius r1 is delta g1. So we are trying to compact the spherical particles of having spherical dimension, in which the radius of the sphere is r1, and then the corresponding driving force on the delta g value will be proportional to, will be equal to delta G1. Okay, then we have case second where the particles, if the particle size is reduced to R2, now we have R2, and this R2 is equal to zero point 0.1 times the R1. Then we have to find what will be the value of delta G2. Okay, we know that your driving force for the sintering will depend on your particle size, and that particle size is inversely, it is inversely proportional to your particle size. So if you know, you can say that your delta G1 divided by delta G2 is equal to R2 by R1. Okay, R2 will be equal to your 0.1 R1, and your R1 is as such given as R1, right? So you can find that your delta G2 is equal to 10 times your delta G1. So this is your final relationship. So you can say that your delta G2 is actually 10 times of whatever the value of your delta G1 is. It is 10 times higher than your first delta G1 if you reduce the particle by 10 times. If you reduce the size of the particle by 10 times, your driving force will increase by 10 times. So the lower the particle size, larger is the driving force. So I think that is all for today.